Let's start with the multiplication rule. Okay, so alright, so now the multiplication rule has to do with procedures or operations, however you want to phrase it. So let's say if an operation consists of k steps, so we have an operation where we have to do k steps, and so we'll say the first step can be done in n sub 1 ways. Okay, so we have an operation that we're trying to perform. The first step can be done in n sub 1 ways. Okay. The second step can be done in n sub 2 ways. So we got our first step and we got our second step. Okay. And let's go dot dot dot. And say that the kth step in n sub k ways. Okay, so there are a certain number of ways that each step can be done. Yeah. So how long, the question becomes, how long could the entire process take? Well, in all these different ways we can do this, but we're doing it as steps. So then the entire process can be done in, so this is going to be multiplication, so this is n1 times n2 all the way up to n sub k ways. Okay, and we actually, I hinted at this problem last time in class. So let's examine one of these problems. So let's say give everybody a sec, just make sure they got that one down. All right, now you have to be very careful with the language when you talk about these probability problems. So, I mean, if you ask the question, how many ways could I find a group of 4 among 36 students? That is a simpler problem, okay? So that would be what? 36, I'm going to choose 4. Okay? That would be step 1 in this problem, okay? So, the previous statement said, all right, so we have an operation. Let's start with that. Just an operation consisting of k steps. And the first step can be done in n sub 1 ways. Okay. So if I say I've got a class of 36 students and I want to divide them into groups of 4, what am I going to do? What is the first possible thing that I can do? Okay, so step 1. And so what is the possibilities for step 1? I've got 36 students. I can randomly pick 4 out of this group. Okay. So what would that amount to? That would be 36, choose 4. Okay? So there's 36 people in the class. I'm allowed to choose 4 of them. That is my first step of dividing the class up into equal groups of 4. Okay? And then I can go to my next step. Okay, so I've already pulled 4 people out of the class randomly. The number of possibilities I can pull is 36, choose 4. Okay, now how many people left in the class? Choose 4. Okay. Now I've pulled 8 students out of this class, and I've divided the number of possibilities of picking the 8 students out of the class, given this procedure. And so what would the next one be? 28, choose 4. What would the next one be? 24, choose 4. And then I would have 20, choose 4. 16, choose 4. And I'm going to run out of room, so I'm going to continue this. Times 12, choose 4. Times 8, choose 4. All the way up to 4, choose 4. And 4, choose 4 just comes out to 1 because I've already picked everybody out of the class that I could possibly pick. So this is the number of possible ways that you could actually take a class of 36 students and then procedurally divide them into groups of 4. Okay, so that is multiplication rule for procedures. Okay. Okay. Now, we have another rule. There's the multiplication rule, and there's also the addition rule. Now, the addition rule so suppose a finite set equals the union of, let's say, k mutually disjoint sets. Subsets. Okay, so we have a finite set that is equal to a union of mutually disjoint subsets, A1 through AK. Meaning that basically they don't contain any intersection with each other. Okay, so if we have mutually disjoint subsets, then if we try to do actually the counting, because this section of the book is on probability and counting, so if we said the number of components of A would equal the number of components of A1 plus the number of components of A2 a base of K. Alright. Now, when talking about this rule is going to be related to two other rules I'm going to bring up in just a second. But what you want to actually observe in this problem, one of the important parts is distinct mutually disjoint. Okay? So the addition rule only works if you have distinct mutually disjoint subsets. Okay? The main part that you want to pick up from that is that what do we mean by disjoint? They do not contain any type of intersection. Okay, we'll deal with intersections here in a minute. Okay. And even the concept of intersection itself is it can be vague, depending on the language that you use. All right. So a question that can go along with this one is, so what I'm going to do today is we're going to go over some definitions and I'll do an example of each one. Okay? So let's say how many bit strings okay. And now one of the things you want to notice on this question is that it says how many bit strings consist of 1 to 4 digits. It's not necessarily asking about the numbers that they represent. Okay? It's just asking about how many actually consist of 1 to 4 digits. So what are we going to end up with? We're going to end up with subsets in this problem of bit strings with 1 digits, bit strings with 2 digits, bit strings with 3 digits, and bit strings with 4 digits. Okay? So the number of elements that would create this set the number of 1 digits, two digits, plus the number of 3 digits. And I'm going to run out of room, but that's a problem with Sharpie. 4 digits. You know what? I'm going to rewrite this on another page because I'm going to run out of page on here. Okay. So let's try to think about this problem. If I was actually going to divide this thing up and to calculate the number of bit strings consisting of 1 to 4 digits. Okay, and I'm gonna just rewrite this real quickly. Okay, so I said number of 1 digit. Y'all don't have to rewrite it, I'm just trying to make room on this page. Because I like to represent things visually. All right, now we consider, first of all, the number of bit strings only involving 1 digit. Well, what do we have from this? 0 and 1. Okay. The number of bit strings involving 2 digits. Okay. And the numbers involving 3 digits. Okay. I'm not going to write down all the 4-digit strings, bit strings. Okay, and now one of the things that confuses people in this problem is they assume that you're talking about actual numbers. Okay, so what are these numbers? That's 0, 1, 0, 1, 2, and 3, and they contain the same numbers, but that's not what the question was asking. It was how many bit strings of digits from 1 to 4 could actually exist. Okay, so when we ask this problem, how many actual ones could exist? Well, what happens on the first one? The number of digits, the bit strings of length 1. Well, there's 2 of them. And the next one would be 2 squared. And the next one would be 2 cubed. And the next one would be 2 to the 4th. That's the number of bit strings that we could have. Okay. Now 16 plus 8 is 24, 24 plus 4 is 28, and then 28 plus 2 is 30. So that would come out being 30. So that is the addition rule, if we're just talking about counting things. Okay. So that's dealing with subsets. All right. Now, but what I mentioned on the previous problem is that what is one of the caveats to using the addition rule? Distinct, mutually disjoint. Okay. But it also says union right here. Okay. So A would be the union of A1 through A sub k. And because of the fact that they are distinct, mutually disjoint, it turns into the addition rule, and we can say, okay, that's just the sum of the number of the subsets. What happens if they're not distinct, mutually disjoint? Okay. Well, in that case, what do we actually end up with? Okay. Okay. So now, the inclusion-exclusion rule and its relationship with the addition rule, okay? What is the main difference between these rules, all right? On the previous problem, well, you can actually view the inclusion-exclusion rule as an extension of the addition rule, okay? So, in the previous problem, it said, okay, A1, A2, all the way up to AK are the unions. A is the union of all of those. Okay, now we're just saying, we got two of them, A union B. What we're leaving out is the concept of them being disjoint. Okay, so if they were disjoint, their intersection is 0. So this would just turn into the addition rule because they would have no intersection between them. Okay. But if there exists an intersection between the subsets, what you have to do is you have to subtract that intersection. Okay, so now why would we have to do this? You have to think about, all right, we're saying the number of elements of A or B. Okay? So, if we look at this graphically, if we look at this at a Venn diagram, the number of elements in A or the number of elements in B. Okay. So if I said N of A union B, all of the elements that exist between the unions of A and B. Alright, so I'm picking up all of A, including the intersection with B. Alright, that's what I'm trying to figure out, is the number of elements in A or B. Okay. The number of elements in A or B would equal, all right, so the first thing that we would have would be the number of elements of A. Okay. And then we would add in the elements of B. Okay, so I'm adding the elements of A and the elements of B. But what just look at this picture and try to ask yourself the question. I'm trying to get to the number of elements of A union B, okay? But if you just look at these two pictures right here, what is the problem that we're encountering is that this intersection period right here, this A intersection B, if we actually add these two together, it's going to be counted twice, okay? Because it's counted twice, then what we have to do is we have to subtract the intersection. So the number of elements of A union B equals the number of elements of A plus the number of elements of B, and then we are going to subtract the number of elements what am I writing C? That's B. Sorry, I'm thinking about the next problem. The next one will include C. Okay. So the number of elements of A union B equals the number of elements of A plus the number of elements of B minus the intersection of A and B. Okay, so that original formula should have been number of elements of A union B equals the number of elements of A plus the number of elements of B minus the intersection of them. Okay? And we just subtract out the intersection because otherwise it would be counted twice. Okay. So let's see how one of these problems, well actually let me write down the next one. There's another rule that involves A, B, and C. That can be done through diagrams like this. It just takes a little bit longer. If you had the number of A union B union C, that would equal the number of elements of A plus the number of elements of B plus the number of elements of C minus the number of elements of A intersection B minus the number of elements of A intersection C minus the number of elements of B intersection C, and then plus A intersection B intersection C. Okay. So let's do a practical problem for this. After everybody writes it down. Okay. All right, so let's say let A be the set of all integers (1 to 100) by 2. Okay. So now, 100 equals 2 times 50. So the number of elements of A would equal 50. Comma right there. And then say, let B be the set of integers from 1 to 100 by 3. All right, now this is going to refer to something we looked at earlier on in the semester. Well, about remainders. Well, 100 is going to equal 3 times 33 plus 1. So the number of elements of B would equal 33. All right. Now, what do y'all think the set would be of the intersection of these? Now, think what's meant by intersection. So when we talk about, well, I'm going to ask about the union of this statement. So the number of elements that are divisible by A or B. Okay. So we've already figured out the number of elements divisible by A. We figured out the number of elements divisible, A is the number of elements divisible by 2. B is the number of elements divisible by 3. What would the intersection of those elements be? I mean, what's the difference in terminology between a union or an intersection? And I'm asking people online as well. Okay, so we got all the numbers between 1 and 100. And so we're asking all the numbers between 1 and 100, how many are divisible by 2? Okay? And then, all right, we ask the question of all the numbers between 1 and 100, all of the numbers that are divisible by 3. And then, so we're saying, well, the number of elements of A or B would equal the number of elements of A plus the number of elements of B minus the number of elements of A and B. That's what's meant by intersection. So what would it mean to be an element of A and B?
Be divisible by 2 and 3.
Yeah, it's divisible by 6. That's it. So the intersection of the number of elements between 1 and 100 that are divisible by 2 and 3. Okay? So, the intersection of these elements, A intersection B, would be So A intersection B would be the numbers divisible by 6. Okay, so we're gonna do the same procedure that we did on the other ones, where we're gonna say, well, 100 would equal 6 times 16 plus 4. So the number of elements of A intersection B would equal 16. Okay, so those would be numbers that are divisible by both 2 and 3. Remember, intersection is our and statement. Okay, so to get the answer to this problem, we need to say, okay, the number of elements of A union B, which would equal the number of elements of A plus the number of elements of B minus the number of elements of the intersection of A and B would equal 50 plus 33, and then we would end up subtracting 16 from this problem. 33 minus 16 is 17. 17 plus 50 is 67. Okay. In the concepts of counting and probability, they work the same way. So, if we talk about probability, the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. Okay, so in the previous problem, we were talking about dividing by different numbers. Okay, a lot of the examples in y'all's book have to do with, well, instead of dividing by 2 or 3, what if we were dividing by 5 or whatever? But let's say we had a deck of cards. We spent a lot of time talking about cards when we're talking about probability. So we've got a deck of 52 cards. And let's say we want to have 2 relationships. We're going to pick a card out of a deck. Okay? So let's say So what is the probability of choosing a base card or a red card from a deck of 52 cards? Okay, so this is probability of A face card or a red card, okay? This is gonna be the probability of picking a face card plus the probability of picking a red card minus the probability of choosing a red face card, the intersection of them. So if you had a queen of diamonds, or a jack of diamonds, or a king of hearts, that would actually, it gets counted twice because we already picked out the hearts and the face cards. So, the first thing we want to look at this is what is our A and B, okay? Let's say, okay, we're talking about the probability of event A or B, okay? So, A would be a face card. All right, and we're going to define a face card as jack, okay, that would be jack, queen, or king. We're not going to include aces. So, the probability of choosing a jack, a queen, or a king, okay? So, there are 4 suits. We have clubs, spades, diamonds, and hearts, okay? There's a jack, a queen, and a king within each suit. So if I have a jack, a queen, or a king within each suit, that would mean there would be 3 times 4, which would be, there are 12 face cards out of the 52 cards. Right? Now B would be a red card. Okay, so what does that mean? You have to be a diamond or a heart. Right, so I'm picking one card out of the deck. I said it has to be a, well, what is the probability of being a face card or a red card? So the probability of choosing a red card, what do y'all think the probability of choosing a red card is out of a deck of 52 cards? Okay, so yeah, somebody said 1/2. Well, yeah, half the cards are red cards, and so there's got to be 26 of them. And I'm just not simplifying because we're trying to consider this just as a sample space of 52 cards. So we'll leave it as that 52 on the bottom. Okay. So yes, we have 4 suits. 2 of those suits are red. So yeah, the probability of picking a red card is 1 out of 2. It's 26 out of 52 because there's 26 red cards. Okay. A little bit trickier of a question is what would A intersection be? Okay. That would be a red and a face card. So, we have to ask ourselves the question, what is the probability of choosing a red card that is also a face card? Okay, so red and face card. That's meant by intersection. So we're gonna have Jack, Queen, and King within half the deck.
6 over 52.
Yeah, it would be 6 divided by 52 because there's only 12 face cards, so we cut off half the deck. That would be 6 divided by 52. So we only have 6 cards within the deck that are both red and face. That would be the Jack and the Queen and the King of Hearts and the Jack and the Queen and the King of Diamonds. Okay. So now the probability of choosing a red card or a face card, okay? The probability of A union B would equal 12 divided by 52 plus 26 divided by 52, and then minus 6 divided by 52, which would equal 32 divided by 52.